For this phase of our development, our group focused on translating our decimal group number 307 into its corresponding 4-bit binary sequences, which is 0011 00000111. Using an Arduino UNO, utilizing a push button to control the execution of the sequence, we set the constraints to represent the strict logic rules that define how the data must be processed by the system. Specifically, it dictates a precise mutually exclusive relationship between the input data, user interaction, and time. When the button is pressed, the system translates the binary data into LED behaviors by blinking the LED for exactly 1 second, when a bit value is 0, and for exactly 2 seconds when a bit value is 1. If the button is not pressed, the sequence remains off.
We set up the hardware from scratch. Firstly, we connect a cable from a digital pin on Arduino board, pin 3 for example, and connect to the end of the positive lane of the breadboard. Then we connect a resistor to the slot above the cable end, link it to the central board, and place the LED into the socket above, ensuring the LED is placed in the positive flag correctly aligned. We repeat this process 3 more times using digital pins 4, 5, and 6. Then we connect another cable to the negative end of all the LEDs and run the cable back to the breadboard's negative rail. To integrate the push button, we wire one of its terminals to digital pin 2 on the Arduino and connect the opposite terminal to the breadboard's ground line. Finally, we connect one cable from the breadboard back to the ground socket on the Arduino.
Issues, we separated segments of the code into variables and created a custom function to handle the LED blinking logic. Instead of repeating the same sequence instructions for every digit, we wrap the main sequence in conditional statements tied to the button states and use a modular function to process the binary arrays. This drastically reduces the amount of clutter and repetitive code. Centralizing these frequent lines of code ensures that we can change the inputs or timing without risking an error that leads to mass failure, while also ensuring the code is easy to read for other users. This modular programming approach not only successfully managed for interactive button logic but also minimized timing errors in the simulation, ensuring that the sequential lighting of the LEDs remain highly consistent and visually distract across the video demonstration.
It's my turn to explain the code for you guys. So first of all, we use a few arrays to declare the LED pins, which is going to be the pins that are going to be holding the values for the LEDs. And next up are going to be each singular number that got swapped to binary. We keep it in an array as well because later we're going to be using it to call for each LED individually. So down here in void setup, we call for each pin to be output, and those pins will be for LEDs using a for loop. And while down here we put a delay, the reason being that if we instantly let it just set up and run, the button that we implemented into our circuit won't have enough time to set up properly, and it will instantly jump into the code itself, and it will start showing the binary without waiting for the button to register. So down here is basically just repeating for letting the LEDs to blink for either 1 second or 2 seconds, depending on if the provided array shows that the LED that is being referenced is going to be showing 0 or 1. So down here, so for example, if it's 0, it's going to be blinking for 1 second, and if it's 1, it's going to blink for 2 seconds, which is already declared
Here's the
here.
demonstration. And our group is 307. So it's 0011, 0000, and 0111. I'll repeat it again. Alright, and that should be about it for my part. Alright, bye.